when we draw our things like this, Lewis structures is what you guys started with. We always include every atom, we show every bond, we show every lone pair. As we start drawing condensed formulas, we start eliminating hydrogens because we assume they are there. Unless explicitly told that a molecule is missing a bond, like it has a charge on the carbon or something like that, we assume that that carbon has enough bonds for this to happen. And so then we start using our skeleton structures just to simplify the number of carbons. We assume the hydrogens are there. And really then, the only thing that is going to be explicitly drawn are heteroatoms. So if it's not a carbon or a hydrogen, it's going to be drawn. So here are 3 complete Lewis structures: 2-methylbutane, ethanoic acid, and cyclohexane. Acetic acid you probably used before, it's the main ingredient in vinegar, right? So when we do this now, we essentially want to make our life easier. So if you guys have done this, how are you guys dealing with these, drawing these condensed structures? Comfortable, not comfortable?
I'm not that comfortable with it.
Okay, Matthew says he's not comfortable, and Beyonce says comfortable. We'll take a quick work on this. So basically, what you're going to do is that every endpoint of a line is going to be a carbon. Every time you reach a bend, that is going to be a carbon. So when we draw our Lewis structures, we are just going to focus on our carbons. So I'm going to circle this. So this is really what we need to draw. So now imagine that I'm simply going to start here, 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 like this. So every time we have an endpoint, I'm going to circle. This is a carbon. I don't know why it does that sometimes. So every time I draw here, this is a carbon. These endpoints are carbons, right? So that's the same as these 3 here. Every time I come to an angle, meaning I come to a point where there more than one line, meets. So this here is going to be this here, and then this here is going to be this here, right? So now we haven't written out carbons. It is explicitly understood that wherever 2 or more lines meet, or at the end point, that is a carbon. Do you see how that works? So now, when I do something a bit larger, right? So when I start doing something like this next one, ethanoic acid, we do the same thing for our carbons. But when we have heteroatoms, a heteroatom is anything that's not carbon or hydrogen, we explicitly write them out. So basically, again, this is the idea of I'm going to just include these. So I'm going to draw carbon to carbon, and then now I'm actually going to write out this oxygen. I'm going to draw the double bond and this oxygen. So then I assume that wherever, again, more than one point comes together, it is carbon. And I'm going to try drawing that second line again because I want that to be clear. Yep. And the only other rule we have is we don't draw hydrogens. Do we ever write in hydrogens? I'll ask you guys, or do we always ignore them? And if you're not sure, that's fine. We ignore them except, there's always an exception, right? We ignore them except when that hydrogen is on a heteroatom. So in this case, we have this hydrogen here. It's not on a carbon, it's on a heteroatom. So then we would draw it out like this. So if that hydrogen is on a heteroatom, then we put it there. Yep, ignore when doing this one except when bonded to something other than C, right? So then our last thing, right, that we're doing is that we, again, are just going to draw our carbons. There are only carbons in here. There are only hydrogens. We don't have to worry about anything else. So then I just go carbon, 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 carbon. So then I can count what's going on here. So 1, 2, 3, 4, 5, 6. I'm gonna go down here and go 1, 2, 3, 4, 5, 6. So I counted the amount of carbons that are in that structure and the number of places where my bonds come together matches, so that makes sense. How do you feel about that, Matthew? Does that help any, or are you still a little unsure?
That helped a lot.
Okay, so that's good. Make sure that you are taking your time. So for this one, it says, sorry, draw the best condensed structure. So I would say if you're really bad at this, try drawing the condensed structure. So what I recommend for you guys right now, like I said, is just think about where the carbons are at. You know, imagine that and try drawing. I'll let you guys do it. I'll give you like 20 seconds if you want to practice, and then I will draw myself. Oh. I'm gonna grab my phone while you guys are doing this. I'll be right back. Okay, so now we're gonna come back to here, and I see I missed a chat. Yeah, we'll go over that too. So we'll make time for that. But just to go over, so functional groups are important, but I will tell you this, Beyonce, is that you're going to be consistently learning about functional groups because there's so many. So what I recommend as an instructor is that, and as an organic student, when I learned organic chemistry all those years ago, make flashcards of the functional groups, recognize what they are, because it's going to make your life a little bit easier. So now come into here, when you do this, I'm just going to circle all of my non-hydrogen atoms like this. Then I'm going to try and repeat that. So 1, 2, 3, 4, 5, 6. And then coming off of here is, so I'm going to circle 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, this is the proper way. This is how you should draw it. You alternate your bonds. But if I was to draw it the same way that they drew it, just so you guys can see, I'll draw with the same relative geometry. This is still the same thing. It's just not drawn as correctly, as properly as it should be. But this is essentially what they are. Hopefully you guys got that. And this is just the idea of how you draw your condensed structures. And again, it's to save time, because when you start thinking about having to draw, imagine having to draw out carbon, having to draw all the hydrogens. A vast majority of your time in this class would just be spent drawing, and that's really not useful. All right. So going forward. So it says, which of the following is the best Lewis structure for CH2CCH3, CH2CH3? So which of these is the best one? Go ahead and put your answer in the chat. Which letter is the best representation? Okay, looks like Beyonce's got D. What about the other three of you? Matthew says B. And I think just Alyssa's here in spirit. In frozen truck spirit. Yep. So Alyssa's got it right there, is that you always want to make sure that your carbons have 4 bonds, right? Unless explicitly told. Like if you had a charge on one of those carbons in the condensed structure, then you have to assume, right? This is what we're doing. We're assuming that every carbon has 4 bonds. So if I look at this carbon here, helps if I turn on the writing tool. This carbon only has, the carbon to the left only has 3 bonds. And again, 3 bonds in a lone pair. And finally, 4 bonds, right? So this is the correct structure. And just to double check, right, it is going to be the bottom one. But just to double check, you just go left to right. So CH2, right? CH2, carbon, right? A carbon with a CH3 coming off, and then I have CH2, right? So CH2, and then CH3, CH3. So that should be the correct one because it matches the formula in terms of what carbon and hydrogens are there, and every carbon has the correct number of bonds, right? So if you're given a condensed Lewis structure that is has a charge or something, or there's a carbon without the correct number of bonds, then that carbon will have a charge on it, like a plus or a minus or something like that. So this is why you guys learned about how to calculate formal charge, because it becomes very important for that. All right. Any questions? You guys good? Okay. So here are basically your rules for drawing your Lewis dot structures. I would make sure that you do this and go over these until they make sense. Again, this is something that, like anything else in chemistry, it's really just practice. And once you understand it, you won't forget it. It's one of those skills that just sticks with you. So make sure you really focus on these. And again, just make sure you're paying attention to, so if you ever are unsure, count the number of carbons in the Lewis structure, count the number of carbons in your condensed structure. Yeah, so Beyonce's saying the problems you have in your textbook, do those ones. That's going to help you. Practice, practice, practice. All right, so now it says draw the, sorry, I have to move my control panel all the way. Draw the skeleton structure for this one. So I will let you guys try this. I will give you about 30 seconds and then I will come in and draw it myself. Yes, I think while you guys are drawing this, Megan, she's the student with red hair. I think she said that the snow was up to her, about to her thighs relative. That's how much snow you guys got. That sounds pretty rough. That's probably about what, 2-3 feet of snow, give or take. That's why you should have huskies and sled dogs, Alyssa. Make your life a little bit easier. All right, so I am now going to draw this out. So it wants us to draw the skeleton structure. So I usually count my carbons that are in a line. So one, oh, help if I turn on the writing tool. Help if I move this down so I can see. So again, I don't know why it does that. So I have 1, 2, 3, 4, 5, 6, 7 in a row, right? So I have 7 carbons in a row. So I go, actually, hold on, I apologize. Let me try that again. So right now, right, I have, yeah, I have 7. Oh, sorry, I'm just looking at this real quick because there is a little bit of, okay. When we were counting ours in a row, I'm sorry, I got confused for a second. We count the carbons that are not in a parenthesis. So 1, 2, 1, 2, 3, 4, 5. We count the carbons that are not in the parentheses, okay? So 1, 2, 3, 4, 5, like that. Okay, so that is our base chain. Now, on carbon 4, I'm going to number here 1, 2, 3, 4, 5. What else is coming off of carbon 4? So what else is coming off of this carbon that I'm going to circle? 2 carbons, right? So this is going to be a CH3. This is going to be a CH3. So that means so far I'm good up to here. Now the next carbon, right, has a hydrogen. It has a CH2, CH3, and an OH. So I'm going to draw the OH first, OH. I don't draw the hydrogen, and then I go CH2, CH3. And so this is relatively what my structure should look like. And just to be sure, I'm going to count my carbons. and say, yep, again, there it does that. I don't know why. Maybe I need to clean off my screen. Maybe my screen's dirty. Oh, jeez. All right. Are the H3 coming off both of the carbons? Yeah, because when it says CH3 and you have this 2 outside, remember that tells you how many of those you have. So just to double check, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So does that make sense? I have all of my carbons there. I have 1 oxygen, which is right here, and everything's there. How did you guys do on that one? Make a mistake or so? Yeah, so when you're thinking about this, always draw the main chain first, meaning look for the carbons that are not in a parenthesis, right? You're just looking at those carbons that are, in that straight chain, and that's what we drew first. And then you go and start adding in everything else, right? If you want, you can add in our heteroatoms. If you want, you can start adding in those things that are coming off. And that's basically it. Does that make sense? Okay, and again, this is something you want to do for practice. Practice, 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 practice. All right, so now I'm going to clear this off. And we are going to just continue on. So now, another question. Which is the correct bond line formula for the following structure? Which of the following is the correct bond line structure? So I'll give you guys, when you guys get an answer, put it into the chat and we'll see what it is. Remember, guys, try to put an answer in the chat. I'm the only one that can see it when this is recording. It's not going to go into, obviously, you may be thinking, boy, I have no idea what's going on, and that's fair. But as we do this now, we're simply going to come in here and I'm going to say, let's count the carbons in our main chain. So 1, 2, 3, 4, 5, 6. All right, so 1, 2, 3, 4, 5, 6, 7. Doesn't seem right. So we're going to say not A. I'll double check that. 1, 2, 3, 4, 5, 6. Yep. And there are 7 carbons in that straight chain. Does that make sense for why A is not a good one? Okay, so now we're going to try B. 1, 2, 3, 4, 5, 6. Okay, B is viable right now. We'll come back to that. We'll do C. 1, 2, 3, 4, 5, 6. All right, C is viable. And then we'll come to D. 1, 2, 3, 4, 5. D only has 5. So we're down to B and C. So now A and D are eliminated. D has too few carbons. A has too many. But the only thing left we have to do is just, we have a carbon coming off of carbon 1, 2, 3, 4, 5, 6. So coming off of carbon 3 is a CH3 right here. So 1, 2, 3, there's no methyl. So this is wrong. 1, 2, 3, we have that methyl, right? And then we have a double bond between carbons 4 and 5. 1, 2, 3, 4, and 5. That double bond that we see here is there. So C is our correct answer. Does that make sense for how you work through and solve that when you're trying to figure out which one it is? Okay. So I will say that you guys are still a little rusty, but that's fine, right? You're still learning it. Practice, 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 and that should be it. Okay. Go ahead and go on. So resonance forms, why do we draw them and what are they, right? So does anyone have a good definition for a resonance form that they care to volunteer? You don't have to. You can say, I don't know. That is always an acceptable answer. You're thinking of, Matt, you're not wrong with our structures with the 3D. You're thinking of like Vesper, but resonance forms, right? So when we draw Lewis diagrams, and fun fact, this is what we're talking about in my honors chemistry class right now. When we start thinking about molecular structure and we start drawing the different ways that things are connected, resonance or Lewis dot diagrams are very useful because they show us connectivity. They show us which atoms are connected to what, where are the bonds, where are the lone pairs, so on and so forth. Very useful. However, they don't tell the entire story, right? And so when we draw a Lewis structure and we want to do resonance, sometimes we can get different things to do that. And so an example of this, right, is imagine I have the acetic ion. Oh, help if I turn on my writing tools. Imagine I have the acetic ion form like this. So imagine that I have this, and then this. So I will ask you, and you guys should know the answer. Is this the correct form, or is there another form, another way that I could draw this molecule? Or is this the only way I could draw this? There's another way, right? Because basically, why did I put the negative charge on this oxygen? So now I can imagine I just rearrange my lone pairs and my bonds. And so now this oxygen has is neutral, but now this oxygen has a charge like this. Degrees of unsaturation, not quite yet. That is important, but this isn't related to this. So here I have these two forms of my resonance. Resonance is just saying that there are more than one ways to draw my Lewis structures. There's more than one way. My electrons are delocalized. That means that my molecule, if I was to actually look at it, if you were able to look down to the scale, it wouldn't be this exactly, but it wouldn't be that. It would be an average of the two. Okay? I am not changing the number of atoms. I am not changing the overall charge. I am not changing the number of electrons. Every compound, every version of this essentially is CH3 COO minus. That is what each of these are. I am just drawing them in different ways because my electrons are delocalized, meaning my electrons don't exist in either state. I can think of them as that way. I can draw them in this, but it's really an average between these two, and that's what resonance is. Does that make sense? So whenever you have resonance, the number of atoms stays the same, the overall charge stays the same, the number of electrons, everything is still the same. You're just drawing a different way. And this is one of the major downfalls of our Lewis condensed structures, is that we can't draw it properly. Now, there is proper notation for this, but it gets a little complicated, and you guys will learn about it a little bit later. But this is just the idea that we have these different forms. And when you think about your structures in organic chemistry, resonance exists a lot. It explains the behavior for so many things. Resonance provides stability. So the more stable you are, the less reactive you are. So this is something that's going to be coming up again and again and again. But, all right, enough of that. All right. So what are they? Lewis dot structures are convenient for representing organic molecules. However, Lewis theory has limitation. Sometimes one structure doesn't completely represent the actual structure, which is what we're saying. In most cases, you have to draw multiple resonance contributors to correctly represent the molecule atom. The actual structure is a hybrid of those resonance structures. Like I said, it's an average of those resonance structures, right? This is basically all I said, and she wrote this out very well. I really enjoyed Jen, really smart organic chemist. Well, smart chemist in general, but she's really good at organic chemistry. So this is what you should remember. I would say if she's putting this information on there, you guys should definitely make sure you understand this, because this is typically a question that pops up in organic chemistry, is that what is a resonance structure? All right, so here we have the example of carbonate, CO2 3 2-. How do we know there's more than one valid Lewis-Dot structure that can be drawn for the carbonate ion? So what's the key indicator that this can be drawn in more than one ion? Do you guys know anything? Yeah, typically if you have a sign, that usually means that you have that can be an indicator. Also, if you draw out a Lewis-Dot structure, and I'm going to draw out this Lewis-Dot structure for this. If I was to draw out one of these forms, and imagine I draw this, and I draw out my thing like this. This oxygen and this oxygen are going to have negative charges. And so if you draw a Lewis-Dot structure and you say, I have to put a charge on something, but I have multiple atoms I can choose from. If that's something you see, then you can tell yourself, well, wait, if I have these multiple charges that have to go on and I have more atoms, why did I pick these two? Why didn't I pick that third one? Right. So this is a good example that you probably have resonance, but having that charge is usually a good indicator that you do have resonance. But that's not always a telltale indicator. You just kind of have to do like this, practice. Again, it's just going to be practice, and you'll start recognizing. You're going to soon recognize a lot of molecules that have resonance. So, what she has here is that how do resonance forms relate to the other? What do they show us as a group? So carbonate, when you draw it out, you have to draw several resonance contributors. So if you draw them, you should be able to get 3 resonance structures. So each of those forms is going to be unique, and they don't actually represent our CO3 2-, our carbonate ion. If you took the average of all 3 of the Lewis structures that we can draw, that is what the actual molecule will look like. So don't forget that. The actual structure is a hybrid of our resonance structures, right? So German Shepherd, and I'm not sure what that dog is to the right. I think that's a lab or a retriever. I'm really bad at telling dogs apart. But anywho, you have this hybrid here. So basically you're just combining, it's an average of these. And this is all a hybrid is. Fun fact, lemons are hybrids. So if you have lemon at some point, that is a hybrid fruit. Most of the fruits you guys eat are hybrids. Our ancestors, when they took up farming, basically, started hybriding stuff. Although I think since we're all indigenous, I don't think our ancestors were big on farming. They were still in the hunter-gatherer phase. Farming was starting to develop, but the rest of you students who are watching this video at a later time, this is more up your alley. We were still rocking the bison at this point, so but we still had wolves. We still have our dogs. So we were making hybrids of wolves and dogs. So we were involved in this. Just you guys were the hipsters of farming. You did it before it was cool. All right. So here we have ozone, O3. And so here you have 2 different resonance forms. So if you look at the resonance form for ozone, you can see that we have those dotted lines, and that represents that there is a bond and not a bond, meaning it's an average of, in one resonance structure there's a double bond, in the other resonance structure there is a single bond. And real quick, just to turn on my camera so you guys can see real quick, if you look, do you happen to notice? You can see there, I'm wearing an NAU shirt. I still wear my NAU shirt. I still wear NAU sweatshirts. I let people know that I am definitely still a lumberjack at heart, even though now I work at a private school. So, but this is the way that we represent these resonance hybrid structures. Those dotted lines show us that it's an average between a single and a double bond, like that. Does that make sense for how this drawing is representing that? Yeah. basically resonance tells us that there's multiple forms of drawing the structure. It tells us that electrons are delocalized. All right. And you may be saying, what the heck does that mean? A localized structure means that electrons are firmly set. The electrons aren't, there's no like weird resonance. They are where they are all the time, like a CH4. Every carbon hydrogen bond is always visible in any Lewis dot structure that we draw. In a delocalized structure, a structure with resonance, it's an average of that electrons, right, where we can find them. So they're not locked into one place, they're spread over an entire area. Does that make sense between localized and delocalized? And if a structure has resonance, it is more stable. The more resonance you have, the more stable your molecule is. So carbonate has 3 resonance forms. It is very stable. Okay. Going on. So resonance forms do not interconvert. They are not in equilibrium, just as mixed breed dogs does have some characteristics of each parents, right? It's not like they are, it's not like you would say what has the paws of a German Shepherd or the head of a thing like that. It's just a mixture of them, right? So you will have different things. So they're not interconnected. So those, it's still just one molecular ion, right? It's just basically that your electrons are delocalized. Correct. It's not changing between the forms. When we draw the Lewis dot structures, we show that it's changing. But remember, we said Lewis dot structures are bad at resonance. So that's why we have to like draw that. Does that make sense? So it's only one molecule. The electrons, you know, we don't have different shapes happening. It's just that Lewis dot structures are really, 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 really bad at doing it. So when we draw Lewis dot structures or our skeletal structures, if we do it that way, we have to show the different forms. Does that make sense, Matthew? Okay. And so here we look at our carbonate. If you look there, essentially, if you took the average of being neutral or negative, my roommate was doing Lewis structures. I told her that's a lie. No, that's not wrong. So if you look here, if I think about it, here this oxygen is neutral. It's negative. It's negative. So 3 oxygens, overall charge of -2 in those 3 different scenarios. So therefore, -2 divided by 3. There's a -2/3 charge on each oxygen. It is an average of these. Does that make sense? Are you guys good with that? Okay. Our time is about to pop up because I don't have the full version. So I'm going to stop this one. And then it is currently 7:42. So I will come back at 7:46. I will start a new room and then we will continue on. All right. So we'll come back and we'll finish this PowerPoint. So I will see you guys in about 4 or 5 minutes. All right.